Welcome everybody to the post-contest discussion of the Leetcode Weekly 404. And this is TLE Eliminators, and I am Abhinav. So, let's get started with the first problem. Okay, so in the first problem, what we are given, you are given two integers, red and blue, representing the count of red and blue colored balls. You have to arrange these balls to form a triangle such that the first row will have one ball, second row will have two balls, third row will have three balls, and so on, like it's shown in the picture. And also, all the balls in a particular row should be the same color, and adjacent rows should have different color. So basically, you have to form a triangle like this, where the first row would be of one color. So you have two colors, red and blue. So if you select blue as the color for first row, then first row would have one blue ball, second row would have two red balls, third row would have three blue balls, then fourth row would again have four red balls, and so on. Alternatively, each row would have different colors, and for each row, the color of all the balls would be same, and number of balls would keep increasing. So if you start with blue, you would have one blue, two red, three blue, like this. So this is what this is the form of triangle you have to form. And for this, you are given number of red balls and number of blue balls. You need to find the maximum height of the triangle that can be achieved. Okay. So let's say you are given two integers. Okay, red and blue. Let's say you are given red as 3, blue as 4. Okay, so what you need to do, you need to form triangles. So you have two options. Either start with blue, okay, and you have one blue, then two reds, okay, then you would have three blues, then you would have four reds, okay. So this way, either you can go this way, or other option is start with a red ball, then have two blue balls, then have again three red balls. Okay, so like this you can go four blue balls. So either you can make triangles like this, or you can make triangles like this. Now you need to find, with the given number of red balls and blue balls, this is the maximum number of red balls you can use, this is the maximum number of blue balls you can use, and what is the maximum height of the triangle you can form. So if you form this triangle, it has height 1, 2, 3, 4. It has a height of 4. If you want to form a height of 5, you would have to again add one more row having 5 blue balls. So now you would form a triangle with an height of 5. Okay. And if you are unable to make like 4, then maybe this would be a height of 3. Okay. So according to number of red balls and number of blue balls, you have to decide what is the maximum height you can make. So what you can do here. So first thing, you can just take these two cases, but like you can obviously see both cases would all be almost the same. You can just swap the count of red and blue. So if let's suppose you are able to make, okay, okay, let's start with this. Let's take this example of three red and four blue. Okay, if you have three red and four blue, first, let's take this case. You try to make a triangle like this. So if you try to make a height of 1, you would have only one blue. That's okay. Okay. Then you would try to make a height of 2. Okay. So two reds and one blue. It's satisfied. You have three available reds and four blues. Okay. Let's try to make an height of 3. You would require four blue balls and two red balls. And you have four blue balls and three red balls. So you can definitely make a height of 3 with this. Now, if you try to make a height of 4, a triangle with an height of 4, you would require 1, 2, 3, 4, 5, 6 red balls and 4 blue balls. But you can have 4 blue balls, but you would require 6 red balls. You only have 3 red balls. So you would not be able to make a height of 4 with this. Now, let's suppose you take this case. So for this case, what's the maximum height we were able to make? It was 3. Okay. Now let's take this case when you start with a red. Okay, so you start with a red, a height of one red ball, possible. Now you try to make a height of 2, one red and two blue. Okay, two blue and one red, it's possible. Okay, height of 2 is possible. Now you try to make a height of 3, you would require 4 red balls and 2 blue balls, but you only have 3 red balls. So you don't have 4 red balls. You cannot make a height of 3 with this. So the maximum height you can make in this case is just 2. So which case would you take? You would obviously take this, because here you can make a height of 3. Here you can make a height of only 2. You need to maximize your answer. So your final answer would be 2. So one way is just take 2 cases and deal separately with them. One by one, just consider you are making a height of 1. So what's the number of blue balls or red balls required? So if you are at an odd index, okay, then so you would start with I equal to 1. How would you compute this? You would start with I equal to 1. So for the height of 1, you would need to add 1 blue ball. Now you would go to I equal to 2. For the height of 2, you would need to add plus 2 to red. Okay. For I equal to 1, you added plus 1 to blue, then plus 2 to red, then a plus 3 to blue. So you would just check if I is odd, you would add to blue. If I is even, you would add to red. You would add a plus I to blue, you would add a plus I to red. Simply. Okay. So just you would check for each height. If you go to some height I, if the number of red balls required and the number of blue balls required, if number of red balls required is less than red, number of blue balls required is less than equal to blue. Okay, less than equal to, then your answer is satisfied. You can take that height. At a case where number of red balls required exceeds this value, or the number of blue balls required exceeds this value, you can just break your loop there, and the maximum height that you got, that would be your answer. So for this, you can just take 2 cases. Start with blue. For odd indexes, do a blue. Even indexes, do a red. Or odd indexes, do then for case 2, for odd indexes, do a red. For even indexes, just add plus I to blue. Okay, like this you can take 2 cases. Or if you want to combine these 2 cases, what you can do in a single case, if you want to do, you can just check. So what is this 2? Just you can just swap the number of red balls required and blue balls required, and then check. Okay, so if let's say you went, okay, let's say C1 is the number of balls required at odd indexes, and C2 is the number of balls required at even indexes. You can keep a count of like this, not naming it as blue or red. Now, if let's suppose C1 is greater than C2, then whichever among red or blue would be greater, you would check that with C1, and whichever among red or blue would be lower, you would check that with C2. And if C2 is greater, then you would check the greater one with C2 and smaller one with C2. So your if condition is basically going to be, you would check the max of C1 comma C2, that should be less than equal to max of red or blue, number of red balls available and the number of blue balls available. So the max should be less than the max of this, and the min of C1 and C2 should be less than the min of red and blue. So if you want to combine both the cases into a single case, you can check like this, and in a single case only you can just combine. So your code would just be, you would just iterate for I from 1 to some high value. Maybe the maximum value blue and red is given 100. You can maybe iterate till 100, but you would basically break at some point. So this maximum limit does not matter. You would just break at some point. And for each I, if you would check I modulo 2 is 0, it means it is even. Then you would do just C2 plus equal to I, else you can do C1 plus equal to I. Okay, so if it is even, you can add to C2. If it is odd, you can add to C1. And then just you would add this if condition. If this condition is satisfied, you can just tell that your height is I now. Okay, you can update your height variable to I. And if this is not satisfied, you can just break your loop. Okay, simply. And so this would be your code. You can just return your height after this. Okay, so you can just take a look at the code now. Okay, I have, as I told you, I just took a variable C1 and C2. So C1 was keeping the count of odd, uh, the number of balls needed at odd indexes. And C2 was keeping the count of number of balls needed at even indexes. And my height, I initialized the height variable to 0. Now I started with I equal to 1. I went till 100, but it would basically break till maybe 10, 20 only. Till 10, maximum 10, 20, the height is going to go. After that, done, because red and blue are given 100 only. Okay, so I took 100, but we would basically break at 10, 15, likewise only at max. Okay, so now if you see I modulo 2, if it is an odd index, you would add plus I to C1. If it is even, you would add plus I to C. Now you would just check if max of C1, C2 is less than equal to max of red, blue, and min of C1, C2 is less than equal to min. So why I'm doing max and min, you are able to understand. Like whichever is greater, you would compare with that with the greater one. Whichever is smaller, you would compare that with the smaller one. Okay. So if you have more red balls available, then if C1 is more, you would assign C1 to red and C2 to blue. If C2 is more, you would assign C2 to red, likewise. Okay, so that's why you are checking, you are having this if condition. If you're not able to understand this, you can just break it into two cases. So if you have case one and case two, in case one, you would have C1 would just mean red, C2 would just mean blue. In case two, you opposite of that, like that you can do. And then if this case is if this condition is satisfied, you can just do height equal to I. And if it is not satisfied, you can just break out of your loop. Once, if you're not able to make a height of 4, let's say, you cannot make a height of 5. Definitely, you would require more balls for that. So once this condition is unsatisfied, you can just break out of the loop. No need to check for greater heights. Okay, and then you can just return your height. So this is the simple code for the first problem. I hope the first problem would be clear to you. Okay, so now what's the time complexity of this code if we want to analyze? So like I'm running a loop from 1 to 100, but it's not O of 100. If you see, when would we break? With the maximum height. So whatever our answer would be, what maximum height can we get? That many times we are going to iterate. So if you have red and blue 100, so let's say at max you would have 100 red balls and 100 blue balls. So if you just look at it, how you are going, you are for odd indexes, you are going 1, then plus 3, then plus 5, then plus 7. Likewise, you are going. And for even indexes, 2 plus 4 plus 6 plus 8. Likewise, you are going. So this is a sum of an AP. It would be of form of some form O of n square and O of n square if you sum up till n. Okay. It would be of order of, the sum would be of order of n square. So this sum is equivalent. So this n square is equivalent to the number of odd balls, which is around 100. So n is the order of root 100 if you like try to analyze. So the time complexity is going to be the number of the maximum height you can get to. So the maximum height you can get to this n is the maximum height you can get to. This would be of the order of under root of red or the under root of red plus blue, you can say. Okay, so the number of red balls and blue balls, it would be order of root of square root of number of red balls or blue balls. So this would be your time complexity of your code. Okay, so anyways, the red and blue are just 100, so you can even take up till 100 or cube of 100 you can go. It's accepted. So okay, so I hope the first problem is clear. Now we can move to the second problem. Now, in the second problem, what we have, you are given an integer array nums. A subsequent stub of nums with length x is called valid if it's satisfied. So you are given an array nums, and what it said, you would pick up a subsequence from that nums. The subsequence is named sub, and that the length of the subsequence is x. Now, this subsequence would be a valid subsequence if it satisfies this condition. What is the condition? Sub 0 plus sub 1 modulo 2. This value is equal to sub 1 plus sub 2 modulo 2. Likewise equal to sub x minus 2 plus sub x minus 1 modulo 2. So, and then if this condition is satisfied, it's a valid subsequence. Now you have to return the length of the longest valid subsequence of nums. Okay. Now it's given the definition of a subsequence. A subsequence is any array that can be derived from another array by deleting some or no elements without changing the order of the remaining elements. So what basically a subsequence is, if you have an array of 1, 2, 3, 4, so you just, it's basically a subset with keeping the order same. Okay, so you can just take a subset of this array. So you can delete some, either pick some elements and delete some elements. So maybe you picked 1, 3, and 4. So 1, 3, 4 would be a subsequence. If you pick 1, 2, and 4, so 1, 2, 4 would be a subsequence. If you pick just 1 and 3, then 1 and 3 would be. The order should remain the same as it is in the original array. And then you can just either pick some elements and delete some elements. So that is a subsequence. If you are not aware about what a subsequence is, this is the definition of subsequence. It's basically, you can say it's a subset of the original array. Now, what you have to do, you have to select a subsequence. Now, what condition that subsequence should satisfy? What does this mean? Let's look at this. So, sub of 0 plus sub of 1. Okay, so, okay, let's try to understand this. Let's take it there and try to understand what this condition means. Okay, so this is what the condition is written there. Okay, so this is the condition. Now let's try to analyze what does this condition mean. Now you are given an array. Okay, so you are given some elements in that array. From this array, you have picked some subsequence. Okay, let's say you deleted some elements of the array and then picked this subsequence. Let's say this subsequence is of size 4, then it would have index 0, 1, 2, 3. This would be the indexing of the subsequence. So x is the size of the subsequence. Now, for this, you would have some elements. Now, this is sub 0, this is subsequence at index 1, this is at index 2, it's index 2. What does the condition say? It says that sub 0 plus sub 1 modulo 2 should be equal to sub 1 plus sub 2 modulo 2. It means the sum of these two modulo 2 should be equal to sum of these two modulo 2 should be equal to sum of these two modulo 2, and likewise until the end. This is the end. So for this, you have only three conditions. So like what it basically means, the sum of any two consecutive elements in the subsequence, if you do mod 2 of that, the value would get that should be equal for all the like pairs of consecutive like consecutive pairs you have in that subsequence. For all of them, the resulting value of modulo 2 should be their sum modulo 2 should be the same. Now, what does modulo 2 means? It just basically tells that the number is even or odd. If the sum is an even, modulo 2 would give 0. If the sum is odd, it would give 1, simply. Okay. Now we are given this condition. So I'm telling this is S1, this is S0, this is S1, this is S2, this is S3. What's the condition we have? We have S0 plus S1 modulo 2 should be equal to S1 plus S2 modulo 2 should be equal to S2 plus S3 modulo 2. This is the condition. This is the condition we have. So what does it mean? It So let's try to analyze. If you have sum of two numbers modulo 2, what all cases can we have? Okay, so we can have a case of if the first number is an odd, second number is an even, or if okay, let's say if both are odd, we can have both odds, we can have both even, we can have odd even, we can have even odd. These would be the only four cases that we can have for the sum of two numbers. So if both are odd, the sum of two odd numbers is an even number. So even modulo 2 would give us 0. If both are even, sum of two even numbers would always be even, it would give 0. If there is one odd and one even, the sum of them would always be odd, it would give 1. This again would be odd, it would give 1. So when do we get a 0? We would get a 0 if the both the numbers are odd either, or both the numbers are even. In that case, we would get a 0. And when would we get a 1? If the parity of both the numbers are different, we can say. If one is odd, one is even, then we would get a 1. Okay. So this is the condition. Now what the condition is for this, for the first two numbers, whatever value we get, that should be same as for the next two numbers. That should be same as for the next two numbers. So let's take this first case. Okay, if it means S0 is odd, S1 is also odd. So this value would be 0. So we can replace in this place we can replace a 0. It means S1 plus S2 mod 2 should also be 0. It means S1 plus S2 mod 2 should also be 0 if this is 0. Now, we already know S1 is odd. So if S1 is odd plus something is going to give you 0, it means their sum should be an even. So odd plus what is even? So in odd, if you add an even number, you would get an odd number. Odd plus even would give you an odd number. If you add another odd number, then only you would get even. So we can just definitely say that S2 is also odd for the first case. So when both the first two values are odd, it means the third value is also odd. Similar way, you can say the S3 would also be odd, S4 would also be odd. So for case one, we can say for case one, when we have S0 as odd and S1 as even, then we can just say that for this case, all numbers are odd. We can conclude this for the first case that all the numbers in that subsequence should be odd. Now, in the same way, let's analyze all the cases. Case 2 is S0 is, what was the case 2? Both even. Okay. So in case 2, we have both the numbers as even. So S0 is even, S1 is also, sorry, in the first case, we had both odd. Okay. So if we had the first two numbers as odd and odd, we concluded that the third number would also be odd, and in the same fashion, all the numbers would be odd. Okay, this is what we concluded for first case. If we have both even, what can we conclude? So it means S1 plus S2 both are even. So even plus even, we would get an even. It means 0. Okay. Then we can say this is S0, this is S1. Then we would say S1 plus S2 should also be 0, mod 2. Okay, both of them should be equal to satisfy the condition. And we know S1 is even. So even plus what would make an even? Definitely even. If we have even plus odd, we would get a odd. So we need to have an even there. So we conclude the third number is also even. So if first two are even, third is also even. Similar way, we would be able to conclude that all the numbers would be even. So in this case, we would have all numbers are even. Okay. Now let's analyze case 3. Case 3 is S0 is what we have odd and even. Okay. S0 is odd and S1 is even. So for different case, what can we conclude for this? Okay. So now here we have uh, this is odd, this is even. So odd plus even would make an odd. Okay. So it would make odd. It means modulo 2 would be 1. Okay. The modulo 2 value would be 1. So it means S1 plus S2 modulo 2 should also be 1. So S1 we know it is even. So even plus what would make 1? 1 means odd. So even plus what would make an odd? So we need to have an odd to make an odd. Even plus odd would make an odd. Even plus even would make an even. So the third value is going to be even. So we had S0 as odd, S1 as even, and we concluded S2 would be an odd. Let's try to think what S3 was going to be. So now we have the condition that S2 plus S3 should also be this same value, 1. S2 is odd. So odd plus what is going to make an odd? Odd plus even is going to make an odd. So we concluded that S3 is going to be even. So we can see that S0 was odd, even, odd, even. So we are going to get a pattern of odd, even, odd, even. So we are going to get a pattern of odd, even, odd, even, odd, even, like this. Okay. For case 4, similarly, if you analyze where S0 is even and S1 is odd, you would realize, so like if you try to analyze S0 plus S1, so even plus odd, you would get an odd. It means modulo would be 1. So it means S1 plus S2 modulo 2 should also be 1. And we know S1 is odd. S1 is odd. So odd plus what is going to make an 1 means odd. Odd plus even is going to make an even. So we concluded that S2 would be even. So even, odd, even, again we would get odd, S4 would be even. So again we would get the pattern of even, odd, even, odd, even, odd, likewise. So like we have concluded for all the cases, if parity of both the numbers are same, so if both are odd, it means all numbers would be odd. If both are even, it means all numbers would be even. If they are different, one is odd, one is even, then we would have alternate odds and alternate even numbers. Okay. So now this is what you are going to, you have concluded. So now you are given an array. You have to take a subsequence from that array. How can you take a subsequence such that it should satisfy either of these four cases? So what can you have? So either you would have all, or you can pick all the odd numbers, okay, or you can pick all the even numbers, that is one choice, or you can pick alternate odd and even numbers. Okay, so this alternate one would just satisfy both the case 3 and case 4. Okay, so either odd even, or even odd even odd. Both of them I am considering as alternate. Okay, so you can pick a subsequence of either of these three types. Okay, either you can pick all the odd numbers from this array, that can be a subsequence. Either you can pick all the even numbers from this array, that would be a subsequence, or you can just pick alternate odd and alternate even. Now you just need to count. For the first case, you can just what's the longest subsequence you can make of case one? It would be just the count of odd numbers in the array, and case 2 would be just the count of even numbers in the array, and case 3 you can count in a way. So you can just start. How can you just tackle this case 3? Let's suppose you have a array 3 1 5 2 4 7. Okay, let's say you have this array. Now for case 1 you would just count the odd numbers. This is odd, 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 odd. So you have 4 odd numbers. Case 1 you get 4. How many even numbers are there? These are 2 even numbers. So 2 even. Case 2 you got 2. Okay, let's try to analyze case 2. So this is case 1, this is case 2. Now how many case 3 do we have? So for case 3 you need an alternate odd and alternate even. So you would just start with the first number. If this, for the first number we can either pick even or odd. Okay, so whatever this number is, you would always pick it. So if it is an odd number, you would pick this. Now after odd, you can only pick an even number. So after 3, if this is odd, you cannot pick odd, you cannot pick. Now it is an even number, you would pick this. Okay, after 3, you pick 2. Now after an even number, you would pick an odd number only. So you cannot pick this 4, you would pick 3. So what you are going to pick, you would pick 3. Now cannot pick 1 and 5 because they are, you would have consecutive odds. So then you have an even number, you pick 2. Then since last number was an even, you cannot pick another even. Then you have picked an odd number. So for case 3, you are going to pick 3 numbers. So it would be 3. Now you would just take the maximum among all the cases. So either C1, C2 or C3. This would be your final answer. Okay, the maximum among all the cases would be your final answer. So you have to just compute this. So in C1 variable, you can just, whenever you get an odd number, just do, you can initialize all these to 0. Okay, start with 0 for all this. Whenever you get odd number, just do a C1 plus plus. If you get an even number, just do C2 plus plus. Okay. If it is odd, do C1 plus plus, else do C2 plus plus. Now, for the case of C3, how you are computing, you can just keep a variable, Boolean variable, which is going to store the last parity. So you can take an F, which is going to store what is the last number you picked was the parity of that number. Is it an odd? Is it an even? So let's say 0 represents an even and 1 represents odd. So for the initial first value, you are definitely going to pick that. So initial, you can initialize it with -1, let's say. It represents that no last value is picked. You can either pick odd, even, anything you can pick. So if you get F, so if the last value is not equal to 1, then you can pick an odd. So if the current value is odd and the last value is not 1, so if it is in the case of odd, if F is not 1, then you would do C3 plus plus and make f equal to 1, so that now the current last value is 1. And for the case of even, if f is not equal to 0, that means the current value we are on is an even and the last picked value was not an even number, then you can pick it. So you would do C3 plus plus and make f equal to 0. So that's what you have to do. This way you can just compute all the three C1, C2 and C2. Okay. So I hope you would have understood the logic of the problem and how we are going to write the code. I've explained the pseudocode. Now let's look at the complete code of what we are doing here. Okay. So my CO is the count of odd, which was C1 in my explanation. My CE is the count of even, which was C2 in my explanation. And my C is just the C3 in my explanation, count of alternate, if you pick alternate numbers, one odd, one even. So these are my three variables, and my F is the parity of the previous index we picked. So currently we haven't picked anything, so f initialized to -1. Now we are just iterating to all the values of the vector nums we are given. So we are iterating to all the values of the array. If we get an odd, so I modulo 2. If this value is 1, if we get an odd, we do p of odd plus plus. And if the previous value was not an odd number, then we will also do c plus plus. It's basically C3 what I explained. And along with doing C++, we'll also do f equal to 1. So we'll just make sure now my previous value is an odd. So next time I would not pick an odd. I would only pick an even number. Okay. So it would just not satisfy this condition if next time I again get an odd number. Okay. So I made C++ and f equal to 1. So this is for the odd case. Now for the even case, I did C of even plus plus. And if the last value picked was not an even number, then we'll do C++ and make the last value even. Okay. So like this, we would be able to compute our uh, the count of odds, count of evens, and the count of alternate odd even length of the subsequence for alternate odd even case. So we'll just take the max of all these three cases. Whatever maximum we get, that would be my final answer and return that. Okay. So I hope the second problem is clear to you. Okay, so now let's move to the third problem. So the third problem is an extension of the first problem only. You can see find the maximum length of valid subsequence 1, and this is maximum length of valid subsequence 2. Okay, so it's an extension of the previous problem. That's the first thing. Now, what's the difference in this? Okay, so for the previous problem, if you want to analyze the time complexity, I didn't do that. So it just we are iterating through all the values in nums and just doing plus plus or anything. So these all are constant operations. So it's O of the length of nums only. Okay, so it's O of the length of nums, O of, and you can say linear time complexity. It's 2, 5. It's accepted. Okay, so this was the time complexity. It's O of n. Okay. Now let's move to the third problem. So what is the change from the second problem you can observe is that in the third problem, the condition you were given, you were given mod 2 here. Only change is the condition is changed to mod k here. Now k is an arbitrary value which you are given as an input. Now this k can be 2. If this k is 2, it would be same as the first one. But now the k can also be 3. It can also be 4, 5, anything. So now for any k, for the given value of k, you need to compute your answer. Okay. So now how would my problem change? Now you can see the constraints. Now the length of nums is 1, 3. So you can apply an O of n square here actually. In the previous case, and now k is also 1, 3. Okay, n square or n into k, something like that you can apply here. In the previous case, n was 1, 2, 5. You cannot apply an O of n square. Okay, now let's see why it's given like that and what change does that mod k makes to our problem. Okay, so now the problem is changed to we are given an array. Okay, so we are given an array. Okay, and we are also given some k. Okay, so this k would be some value of k we are given. Now the condition is you have to just pick some subsequence from that array, select some of the elements so that if you have formed this subsequence, let's say you have formed this subsequence, the condition it should satisfy is S0 plus S1 modulo K should be equal to S1 plus S2 modulo K should be equal to S2 plus S3 modulo K, and likewise until the end. Okay, so now the condition is for all the two consecutive elements, the sum of them mod K should be equal. Now, what do you mean by sum mod K? Okay, let's take an example. What can you have? So let's say S0 is 5, S1 is 7, and K is 4. Okay, so you would have 5 plus 7 modulo 4. It would mean 5 plus 7, 12 modulo 4 would give you 0. Now, if you had an 8 here, you would get 5 plus 8, 13 modulo 4, it would give you 1. Okay, so whenever you do a mod 4, the first thing you can break down this equation into is you can just do a mod 4 with the individual values first, and then you can do a sum. So if you know the property of mod x plus y mod m is same as x mod m plus y mod m. Okay, so we are going to just use this property here. Okay, so if you use this property, what we can say? We can just write this condition that we have. We can change it to S0 mod k plus S1 mod k modulo k. This thing should be equal to S1 mod k plus S2 mod k whole mod k. Okay, this should be equal to likewise. We can change this condition like this. Now, what does that mean? It means whatever subsequence we have, first we for each element we are going to do a mod k for each element. Okay, now just do a mod k for each element. If you have a 5 and if you have a 5 and k is equal to 4, just do a 5 mod 4 and reduce this 5 to 1. Okay, so if you have S0 equal to 5, just reduce it to 1 after doing a mod 4. That's the first thing we're going to do. So after doing this, each element of the array would be reduced to a range of less than k. That's the first thing. Now, you have reduced this value. Let's say you have k equal to 4, and let's say k is 4. After doing S0 mod k, you can either get 0 or 1 or 2 or 3. Among these four values only you would get. So let's say you get a 2 here, and then S1 mod k you got a 1 here. If you got a 2 and a 1, then this sum would be 3. It means this sum should also be 3. Now, if you have a S1 here, you would have again, so S1 mod k was 1, here also S1 mod k would be 1. Now, 1 plus what would make a 3? So, 1 plus, so what's the condition? 1 plus the value of S2 mod k is going to make a 3. So, S2 mod k should be 2. Okay. Now, here you had S2 mod k plus S3 mod k whole mod k. Okay. So what would this be? So now again, this should be equal to, now S2 you got, S2 should be 2. So this S2 should be 2. S2 plus what is going to give you a 3? All those should be equal to 3. S2 plus what is going to give you a 3? It should be 1. So what you can see, S0 mod k is 2, S1 mod k is 1, then S2 mod k is 2, S3 mod k is 1. So you're getting 2, 1, 2, 1, 2. You can just prove this for any case, you would get a alternate pattern only. Like for the odd even case in the previous question, we had gone an alternate pattern. Now you can just generalize this for a mod case that whenever you have S0 plus S1, if let's say this is now instead of 2 and 1, let's say I'm telling this is X and Y. Okay. Let's say I'm saying S0 mod k is X and S1 mod k is Y. So their sum would be X plus Y mod k. Okay. So if either this x plus y would both x and y are less than k. So either this would exceed k, and so by doing mod k, it would be reduced to x plus y minus k, or it would remain x plus y. So it would be either this or this. Okay, any one value, this x plus y mod k. Now, S1 is definitely y. Y plus what is going to make you x plus y mod k? It's definitely y plus x is going to make an x plus y mod k. And then if S2 is x, then x plus what is going to make x plus y mod k? Definitely y. So you can just prove that you would have a xy sequence. And if this x and y are equal, you would have x sequence. Okay. So that's what was happening in the previous question. If you like prove it in a general way, that if you had an odd even, then you had odd even, odd even, odd even. If you had odd odd, it means both x and y were same, so you had all odds. If you had even even, both x and y were same, that's why you had all even. Okay. So you can understand the previous question also from this case. Okay. Now, uh, once we have found out that you are definitely going to have an xy like this, an alternate sequence. Now, but the problem here is that if you have, let's say, k equal to 4, let's say k is equal to 4, what combinations of xy can you have? You can have 1 and 3. 1 plus 3 would, like, you can just have anything. No? Like, let's say you take x equal to 1 and y equal to 2, then 1 plus 2 would be 3. You can have 1 2 1 2 1 2 1 2. All the equalities would be equal to 3. Or you can have x equal to 1, y equal to 1, both 1 1 1 1 1. All the equalities would be 2. In this case, all the equalities would be 3. Here, all the equalities would be 2. Or you can have x equal to 1, y equal to 3 also. Here, all the equalities would be 4 mod 4, 0. Okay. Or you can also have x equal to 1 and y equal to 0. Okay, so if you see, if you have a k, how many possibilities you can have? For x, you can have 0 to k minus 1. For y also, you can have 0 to k minus 1. So actually, you have k square possibilities, k square pairs of x and y here. So if you like try to analyze for each, so one solution of this, just go to all the possibilities of x and y. Okay, let's go to each pair. So you have k square pairs. Okay, so let's go to each pair of x and y. For a particular pair of x and y, you just fix that. That's what we are counting for this x and y. Then you can, for a fixed x and y, you can just iterate through the array like we did for the alternate case in the previous question. You can just, if you get an x, then go for a y next. If you get a y, then go for an x next. Okay. Likewise, you can, if you have an x, you get something else other than x and y, those are ignored. If you get another x, that is ignored. If you get a y, then that is taken, and then you would search for x. So, but this way you have k square possibilities, and by going through the array, you are doing another O of n. So n into k square, you are given n as 1e3 and k also as 1e3. So this would be O of 1e9. So this would give you TLE. Okay. So this approach is going to give you TLE. So you need to optimize this approach a little. That's what you need to do. So in order to optimize it, so one way to do this is using dynamic programming. You can optimize it using, so what solution I came up with, it is an DT approach. So now let's discuss what you can do here. Okay. So for this, the first thing that we did, we found a pattern. The pattern is going to be XY. Okay. So, but what is this X? These X and Y are the values of the, not the value of the array, but the value of, if the I'm saying the array is A, then it's AI mod K. Okay. So the first thing is you are going to do is for every I to nums is the array we are given. For every element, the first thing you would do is just do I mod equal to K. Okay. So if you have K equal to 4 and you have an element 1 and an element 5, does it make any difference? You can reduce both of them to 1 because 1 mod 4 is also 1, 5 mod 4 is also 1. So the only thing is you care about is mod k. So you can just reduce every element. So if you look at the problem statement, the range of nums I was given up till 1 is 7. But if you do a mod k to every element, you would reduce it to 1e3. Okay, so you would reduce it to k. You would have a maximum range of k. It would be less than k. Okay, so you can reduce this each element from 1e7 to 1e3 by making a mod k. That's the first thing you did. So you first reduce every element to I mod equal to k. You performed this operation first. Okay, now you have an array where each element is less than k. Okay, you have nums I less than k for every I because you have made a mod k for every element. And you have the length of the array of, let's say, the length of the array is n. Okay, and n is up till the range of 180. So now what can you do here? Okay, what you so now what I'm going to do here, I'm going to take a dp. Okay, so as you can see, we have 1e3, so we can comfortably do an o of n square or n into k, something like that. So obviously we are going to take a 2d dp. So the first state of our dp is going to be I. So I would be So I would be the and would represent an index in the array. So in most of the cases, whenever we take a 2D DP or 1D DP, the if we are taking an index in one of the states, in generally we take an index as one of the states. What does it represent? It just represents the subarray from 0 to I. Okay, so we are just calculating our array. So we are dividing this array into subparts. So first we would calculate our answer from 0 for the subarray of just 0, then subarray 0 to 1, subarray 0 to 2, subarray 0 to 3, subarray 0 to 4. Likewise, we are dividing this problem into sub parts. That's what we do in DP. So first thing is my index I represents that I'm calculating my answer for the subarray 0 to I. Okay, for this subarray, I'm calculating my answer. And then in the second state, what I can have, okay, let's say I'm saying that if I'm calculating for this subarray, I'm saying that let's suppose this ith index, whatever ai I had at this, let's say I had an x here. Okay, the value at that ith index mod k was x. It means, let's suppose we have picked this value. Okay, let's suppose we have picked this x, then we can just iterate through all the y's we can have. Okay, so the second state we can have, that can be, you can say, y. Okay, so it just represents that if we pick that ith index, then what's the for the subsequence that we are making, if we pick that ith index, then definitely out of x and y we are going to have alternate xy xy xy. So it means we have picked an x here. Now what is the y? So we can have all the combinations of y from 0 to k minus 1. So we would iterate from 0 to k minus 1. So let's say we have fixed a y. Now once we have fixed an x and a y, we can compute our the length of the subsequence. Okay. So the first is the state that we decided. What does this state represent? It represents that my maximum subsequence. That's what we would always find. That's what we need to find. We need to find the maximum subsequence for the whole array. So for the DP state would also be a maximum subsequence. So our answer, it's basically our answer for the subarray 0 to I. Okay. So for this subarray from 0 to I, for this subarray, if we have picked ith index, so I'm fixing it that we have definitely picked the ith index. So for the final answer, we can just iterate through all the I. So there would be some index which would be picked. So the answer for that index being picked would be one of our possible answer. So we for the final answer, we'll iterate through all the I's and then we'll do the max of them. Okay. So this I is basically the last index that is picked for our answer. Okay. So if we have picked the ith index and y is the other value of our the alternate subsequence that we have. So y is the other value in our subsequence. So this is what my DP state is. So like whenever you are writing a DP solution, the most important thing is to write three things. First is the state. This is our state. You should be clear what your state represents. If you're clear what this I and Y, what this DPIY represents, then you can clearly write your transition. The next step to solving the DP problem is writing your transition. So for writing the transition, you should be clear what your state is. According to that, only you would write your transition. So once you have written your transition, then you just need to write your base case and then you can form your complete solution. Okay. So now let's try to look what our transition is going to be. Okay. So now since we have taken this state, what I can write for my transition? Okay. What is my DPIY? Okay. So here what we have considered, I'll make it a little more clear. So we have taken a DP. Uh, Okay, let's say this is our array nums, which we are given in our input. So DPIY represents that we are on the our, let's say this is the ith index. Okay, let's say this particular is the ith index and we have the value here as x. So I'm telling that nums I is x. Okay, so you should just keep it clear that I is not the x, nums I is the x. Okay, for the state we are taking, I is the last index value which we have picked. And what's the actual value at that index? It is nums I. With so nums I is your x. That would be the value of the that would go into our subsequence. Okay, so this is x, and our other value is y. Okay, so what does this? So if you have an x, so what would my DPIY represents? So we can say for this subarray, we have picked this x. Now we are just picking some y, some x, and like this was the maximum subsequence we can make. So how would you write the transition for this? So if we have picked x, it means before picking x, the last picked element was a y. So we can just go to all the y we have before x. Okay. So what is the last y we had before x? Let's say the last y you had before x was at some index j. Okay. So you can write your transition as that dp up till here. So if you take the dp where you have picked this jth index, which had the value of I, and the other value was x, then you can just take this dp, add a plus one to that, that would be of this dp. So you can actually write that your dpiy is, so I'm telling that j is the last index of a y just before I. So just before this index, what's the last y we found? Okay, that is j. So I can write this dpiy is dp of j. So j is the last index picked for this dp, and the other value should be x. What is x? X is nums I. So for this dp, I was saying the other value is y when I was picked. Now when j is picked, I would say the other value is x, which is nums I. I would say nums I. So this dp plus one because this is now taken. Okay. So this would be your transition actually if there is a y present just before x. If there are no y present before x, you cannot pick a y, then your dp of iy would just be 1. Just pick this element. It would be 1. So this value would be 0 if there is no such j present, which is less than I and nums of j is y. Okay, so what's that j? Did you get what the j is? So I'm telling this j is such that nums j is equal to y and this is the greatest j which is less than I. Okay. So the greatest j just before I such that nums j is y, that is my j. So if you can find this j, then you can write the transition as this. Okay. So what's my transition? dpiy is dp of j nums I plus 1. Now you need to find this j. So one way to find this j is just if you are at index I. So if you are at this index I, just go to I minus 1, I minus 2, I minus 3 likewise. Whenever you find a y, whenever you find that nums j is y, then that would be your j. So for that you would write the transition. But this may take a O of n time for the transition. And if my transition is O of n and my state is already n into k, so then my final time complexity would become n into k into n. So this would again give me a TLE. So I need to write this transition in O of 1. How can I do that? How can I find the last? How can I find this j? That's my only problem. So if I can find this j in O of 1, I can write this transition in O of 1, and then my n into k time complexity solution would work. So what we can do to find this j is, so we are iterating from 0 to n, like this we are going. So whatever value we get, so let's say we at some point we got to a value of z. So we can just store a map or a vector where what we can do, we can just update the last index of that value. So we can let's take a last, this can be a map or a vector of size k. What this would store, it would store the last. So last z would store. So I'm just keeping a map of last. So what does this last represent? So last of val, let's say I'm telling val, last of val just represents the last index where, so it's just showing the last index where we got val. Okay. So this is just storing the last index where we got a value val. So now we can just say j is last y. So this is the last index where we got y. You can initialize this last array to -1. So if we get a last y as -1, it means we didn't get a y. We can just replace this thing to 0 if we get last y as -1. And if we don't get a -1, it means we got something, then we can write, we can find that j and write this transition. And after iterating through, like if we have iterated through the ith index, we can just update that last of nums I is I. This way we can just keep our last, this map, we can keep this map updated. By after iterating through the ith index, we can update that value as I, we can map that value to I, so that when we go to any index greater than I for the next indexes, we have stored that if we need a nums I as a y, then we can get it from this map. So this way we can make the transition in O of 1, and the whole time complexity would be O of n into k, and we can write our dp. Okay. So that's what in the transition we were doing. So in that, this is my transition where I'm computing this j as this. Okay. And then I'm also updating my map. So I'm updating my map through this thing. Okay. So my transition is this. And for finding the transition, I have to find this j, which is found like this. And for finding the j, I have to maintain this map. I'm maintaining this map like this. So this can be the things we are going to write inside our loop. Okay. Now just let's analyze the base case quickly and move to our code. So what would be our base case be for transition? So we can just write for the, okay, we have an array. For the 0th index, let's say we have a value x here. So what would my DP states for this 0th value be? So like basically you can even before the 0th case. So what's my transition? My transition is actually just requiring a j, and then this I'm iterating through all the values, possible values of y. So this y is actually from 0 to k minus 1. Okay. The dp I'm having, the size of the dp is actually n into n cross k. Okay. This is the maximum. This I is up till n and this y is up till k. Okay. This is our dp. So for the transition, we are only requiring dpiys, dpj, and num side. Okay. So if we have some j before where we have picked, uh, then we would have this. Otherwise, we would have a one. So this only becomes our base case. If we have for any y, if we have such a j where j is minus one, then we would have dpiy equal to one. So you can actually like there you can just skip this base case and just write no base cases. In the transition only you can check that if j is minus 1, you would just write dp of iy as 1, else you would write the whole transition. Okay, whatever I wrote. That's in that way, if you write the transition, you are just covering this base case alongside. So your base case is just, you can say that for the map of the last map you are telling, that map would be initialized to minus one. That's the only thing you are just going to do for the base case. And then this thing you can cover in your transition. Okay. So you have covered your state. This is your DP state. This is your DP transition. And for me writing the transition, you are requiring another map, let's say. So this is the map computation. And for base case, you are just initializing the map to minus one and no more base cases. So now you can just look at the code, how I'm doing it. Okay. I hope the solution would be clear to you. I've tried to explain it in very detail. Okay. For any DP solution, the thing you need to understand is the state and the transition. If you're clear on the state and the transition, and then you can writing the code would become really simple. Okay. So I'm doing an iterative code for the DP. Okay. If you want to write the recursive code, the problem there would be this map or the vector that I'm storing for calculating my state. I would not be able to store this map for the recursive way, because in iterative I'm going from starting from 0 and going up till nth index. So I'm able to update this, so and use this. But in recursive, the I'm going from the top down approach from n to 0, and it's not in order. Okay. So first you are going to the depth, and then so you won't be able to do and write a recursive code with this approach. You can only write an iterative code with this approach. Okay. So maybe there could be a recursive solution for this, but for the approach that I came up with, I can only write an iterative code. So I'm explaining that currently. If somebody gets the recursive approach, you can write down in the comment. Okay. So the first thing what I did, first as I explained, I went to all the indexes of nums, all the values that I had in my array nums, and I just did a mod case. So I reduced all the values to, so I just reduced all the values to below k by doing the mod k. Okay, that's the first thing I did. So I mod k. Now all the values in my array are less than k. So all the values are in the range less than k in the up till 1e3 only. Okay. So my state, one of the state was k. Okay. So if you had values greater than k, this would create a problem, because in the second state, I'm writing a value which is the value of the array. Okay. So you can understand that. So you need to do a mod k first. Now I've initialized my DP of n into k. I've taken n into k, and initially I've stored 0 in my DP. So that can be skipped also, maybe. If you don't store a 0 also, you are just calculating your DP every time. So it doesn't matter. You don't need to initialize it. Okay. Now I've made this map or a vector, you can say, last of size k. So it just denotes that last of any value would denote the last in occurrence of that value. So initially the last occurrence of every value is -1, and no value has occurred up till now. So now we would iterate. So whenever you have to write a DP solution, iterative DP, if you have a state of n cross k, just iterate I from 0 to n and k from 0, and the other I, j, you can say I've taken val as the variable here from 0 to k. Okay, so iterate two variables from 0 to n and 0 to k. Now, it depends if your transition is taking the help of uh, future values, then you would iterate from the back. If it's taking the help of past values, you iterate from forward. So here, my transition was taking the help of past values, so I'm iterating in the forward direction. I'm going from bottom up approach, you can say. Okay, so now I'll iterate from 0 to n, and this val would iterate from 0 to k. So my dp of I val, so this val is y that I explained there. It is y actually. Okay, what I explained there. So I'm writing that y using val. Okay. So now what is my transition? My transition is dp I val is dp j comma nums I, and j is last of val. So this is my transition. So what I had written in my transition there, so you can have a look. My transition was dp iy was dp j nums I plus 1, and this j was last y. So that's what I have written. dp iy is dp last y nums I plus 1. So dp I val is dp last val nums I plus 1. So this is my transition. And when would we write this transition? When this last val is not minus 1. If this last val is minus 1, we will simply write dp I val is 1. Okay, so if this is minus 1, we will write 1, else we will write the whole transition. And okay, let's ignore this thing for a moment. And then I am updating this last. So once I have iterated through all the values of dp I and then all the values for the ith index, I would update this ith index for my map. So last of num size. So in this way, we are calculating our dp. Now, what my final answer is going to be? My final answer is going to be just the, okay, what we need to compute in my final answer. Okay, so if we have this array and my dp state is showing for this subarray, if we pick the ith index, and then for this subarray, if we pick the ith index, and for that also, I'm going to all the values. So if we just take the maximum of this whole 2D dp, what we get for every element of that dp. Okay, so up till this, if we pick this and take some other value as my y, if we pick this and take some other value as my y, pick this and take some other value as my. So if I take the maximum of all of these, I would get my final answer of the largest subsequence that I can make. So my answer is just going to be max of just all of dp of I, y, max of this. So I would iterate for I from 0 to n and y from 0 to k. So I would iterate I from 0 to n, y from 0 to n, and whatever states we are getting, just take the maximum of all the state. That's our answer. So either you can compute this answer after calculating your dp, you can just run another loop from I to n and 0 to k and then take the max, or I'm just after computing any state, I'm just taking the maximum here only. So I'm just doing this answer equal to max of answer from dpi well here only. So, and I'm initializing my answer to 1 because worst case, what I can do, I can just pick up any element and that would set. If we have only one element, that would always satisfy the condition because there are no two elements or no condition. One element will always satisfy the condition. So one is our answer for any minimum case is one. At minimum, we would always get one as our answer. So that's why I'm initializing with one and then taking the max. Finally, I'm returning my answer. So this is my solution. So I hope you would have understood the third problem. Okay, so now we can move to the fourth problem. Okay, so let's move to the fourth problem now. So in the fourth problem, what we are given, find minimum diameter after merging two trees. So it is a tree problem. So it's an interesting one. So what you are given here, there exist two undirected trees with n nodes and m nodes. So the first tree contains n nodes, second tree contains m nodes, and we would already know, you would know the property of tree that if a tree has n nodes, it would have n minus one edges. and here it's given that they are numbered, they are just zero based index numbered from 0 to n minus 1, 0 to n minus 1, and then you are given the edges. So a tree having n nodes would have n minus 1 edges, a tree having m nodes would have m minus 1 edges. So you are basically given the a 2D integer array of edges. So for the first tree you're given all the edges of the first tree, and for the second tree you're given all the edges of the second tree, basically in the form of AI, BI. So node AI and BI are connected by an edge. Indicates there's an edge between AI and BI. So now you are so basically you are given two trees as an input. Now you must connect one node from the first tree with another node from the second tree with an edge. Return the minimum possible diameter of the tree. So like you are given two trees here, and what you need to do, you need to like connect maybe one node of a tree with another node of the other tree. So you can just pick any one node from the first tree and one node from the second tree, and you need to connect these nodes. And you have to pick such nodes so that after connecting, the final tree that you got, it should have the minimum diameter. That's the problem. So return the minimum possible diameter of the resulting tree. Now, what is the diameter of a tree? The diameter of a tree is the length of the longest path between any two nodes in the tree. So the diameter of tree. So let's see. Let's suppose we only have the first tree. So for this tree, what would the diameter of this tree? We can say this is the longest path in the tree. So we have to pick such a path so that it is the longest path possible in this tree. So for this case, we can pick a path like this. It would have a length of 1 plus 1, so a 2. So 2 would be its diameter. We could have also picked a path of this. It would have also 1 plus 1, two edges in it. So it would also have 2. So the maximum possible path here is actually 2. So this tree has a diameter of 2. If you look at this tree, maximum path is only one path exists here. It has a diameter of 1. Now, when we combine these two trees, let's say we combined this node with this node. So the tree we got, we need to find the diameter of that tree, and we need to minimize this diameter. So if let's suppose we combine like this, the diameter of this tree would be, you can go like this here, then you can go here and here. So this path would have 1 plus 1 plus 1, a total of 3 edges in this path, so a diameter of 3. So this is the longest you can have for this case. You can go like this also, you would have 3, like this also you would have 3. So for this case, this is the maximum possible if you connected these two edges. So if you connected these two edges, you would have a diameter of 3. Now let's suppose we connected these two edges. Now, what diameter you can have? You can have 1, 2, 3, 4. You can have a diameter of 1, 1, 1, 1, a total of 4. So, if you connect like this, you would have a diameter of 4. So, what's the best case? The best case was to connect it like this so that we get a diameter of 3. Okay. So 3 would be our answer for this case. Okay. So, if you see, our answer for this case was 3. If we connected this 0 with this 0, so it's 3 by connecting node 0 to any. So if you connected this 0 with 1, then also you would get a diameter of 3. If you connected this 0 with 1, then also you would have 1, 2, 3, a diameter of 3 only. Okay, so that's our answer. Now, this is the problem what we need to solve. We need to just connect these two trees with a single edge so that the diameter of the resulting tree is minimized. That's our problem. Now, how can we solve this? So if you look at the constraints, the n and m are till 1e5. So number of nodes are 1e5. So you cannot go n square or something like that. You have to do the complexity of O of n or n log n at max. Okay. So now what can we do here? Okay. So let's take the second example. It's looking good. So let's uh, take it there so that we can understand. Okay. Okay. So now, if we have this example, now what you need to do here is you need to maximize the diameter of a tree. So, like before connecting these trees, let's try to understand what diameter of a tree is and how do we calculate the diameter of tree. So if you try to look at what the diameter of a tree is and how we calculate that, you then maybe you would able to get some logic what can we do to minimize that diameter if we are connecting to this. So let's try to first understand, like for any tree, if you are given any tree, how do we compute the diameter of a tree? So let's say you are just given any tree. Now how would you compute its diameter? So what you basically do is to compute the diameter. So diameter is basically the longest path you can have in your tree. Okay, it can be this, that, any path. So the longest path you can have in your tree. So what we would say that we'll just go to all the nodes. Let's say I am at this node. Then I would find the longest path through this node. What is the longest path I can have through this node? If we compute this length for every node, then we can just get the max of all of them would be our longest path in the whole tree. That would be our diameter. Okay, so to compute the diameter, what we do is like we start from the root. It's basically the concept of DP on trees, you can say. We start from the root. Now for this whole tree, the root represents the whole tree. If you are at some other node, it would represent this subtree. Okay, that's what I'm telling. So if we are at the root, it would represent the whole tree. So for this whole tree, what is my diameter? Let's try to calculate that. So for this whole tree, for any node, if that node is the root, your diameter is basically, so if you have a node that is a root and it has some childs, let's say, and every child has some subtree. Okay, so this I'm representing a subtree of this child. Okay, so what would my diameter be? So for diameter, what I would say, not diameter, I would say what's the longest path passing through this node. So we definitely have to include this node. What is the longest path through this node? So through this node, we would come from somewhere, from some path to this node, and then we would go back to some path. That's what we would do. So which path would we choose? To have the longest path, we so among all the subtrees we would have, to whichever child we get the maximum depth. Let's say at this child, if we calculate the depth of this child, what does the depth means? So if we are at this node and we want to calculate the depth of this child, it would be 1, because at max we can go to a depth of 1. If we are here, what's the maximum depth? It's 1, 2. We can go to a depth of 2 at max. Okay, or 1, 2. In this way also we can go to a depth of 2. But if we go here, we would go to a depth of 1. So the maximum depth among all the paths is 2. So that's what I'm telling. So my depth of x just represents that if we are at a node x, then what's the maximum depth we can go from there. Okay, that's what I'm writing by depth of x. Okay, so what's my diameter for a, not diameter, I'm saying the longest path. What's my longest path including this node? It is actually the among all its childs. We would calculate the depth of all its childs. Let's say the depth of the first child is 1, depth of second child is 2, depth of third child is also 2, and the depth of fourth child is, let's say, 4. Then what would my diameter be? I would pick the those childs having maximum depths. So I have to pick two childs, because from one I would go and then I would return to another. So I would pick the top two. So here the top two are 4 and 2. So I would pick like this. So I would start from one of the depths, one of the childs, and go to another child. So my diameter of tree is going to be this far. So in this path, I would get two edges, like not two edges in this child, plus one, and then plus one, and then 4 here. So actually, my diameter is going to be, if among all childs, I am telling that mx1 is the maximum depth among all child and mx2 is the second maximum depth among all childs, then we would say diameter is mx1 plus mx2 plus this and this 2 edge, also plus 2. So that's what our diameter is. Or we can just say, let's say if it has only one child, then what my diameter would be? Not diameter, it's the longest path through the node. It's not diameter, I would say the longest path through x. Okay, through, if you're calculating for node x, I'm telling the longest path through node x. Okay, that's what I'm telling. That would be mx1 plus mx2 plus 2. So if it has only one child, then it would be only this path. So if it has only one child, so and the second maximum is 0, you can say no child, it means a depth of 0, you can say. So then its value would be just this maximum mx plus 1. So it would be mx plus 1 only. So writing this plus 2 is not always correct. You can say the longest path is, you can say mx1 represents the max among the depth of any child, maximum depth of any child, plus 1. I'm storing that plus 1 in mx1 only. Mx2 is the second max depth of any child plus 1. Okay, so then I can say longest path is mx1 plus mx2. If it doesn't have a two childs, then mx2 would be 0. So that we can say. So I'm adding this plus 1 in mx1 only and this plus 1 in mx2 only. So that I can say this mx1 plus mx2. So this is actually what my diameter is, like my longest path for a particular node is. And what my diameter is among all the nodes. If you compute the longest path through every node, the maximum among them is my diameter. Okay, so my diameter is the maximum among, for all the nodes, the maximum path for all the nodes. If we compute the max of all those would be my diameter. So, and I'm telling the maximum path is, we would just go to all its children. The top two depths, the sum of the top two depths would be my maximum path. Now, how can we compute this depth? Okay, that's also a thing. How can we compute this depth? Okay, so to compute this depth, we just simply use DP on trees. So if I'm telling, I'm at this node. Okay, so if I'm telling, let's say, I want to compute the depth of this node. Okay, or the depth of this node. I would say the depth of this node would either be through this child, or through this child, any one child. So I can compute the depth of this subtree. For this node, I can compute the depth plus 1. Either would be this, or this depth plus 1, or this depth plus 1. So I can just simply write the transition for my depth is my depth at any index I. Okay, that I can say as the maximum of depth of j, where j is a child of I. So, okay, j is child of I. Okay, maximum among all the j, depth of j plus 1. Okay, so we'll go to every child, whatever the depth of that child is plus 1. So the max among all that would be the maximum depth of this ith node. That's how. So like this we can just compute our depth for every node. If we have computed the depth for every node, then we can say the longest path for every node I, as among all its child we can see the depths of all its child and take the max 1 plus max 2. That way we can calculate the longest path for every node, and once we have calculated the longest path, my diameter is just going to be the max among all the longest path. So all the longest path of I, whatever we have, the max of all of them would be our diameter. So like in 3 steps we are computing the diameter, but basically if you write a function, you can just do all these 3 steps in a single step only. You can just, this depth would be your dp, so you can compute this, and then you can also write this longest path and just take the max of all of them for the diameter. So you are not storing this basically. So just if you want to compute the diameter, you will not store this longest path of I. You would just take the max among all this mx1 plus mx2. You would take a variable diameter and just maximize it with all these mx1 plus mx2 values. That would give you the diameter. So in one DFS traverser only you can just compute this diameter. But here the question is, you are not given a one tree and just compute its diameter. You are actually here you are given 2 trees. Okay, so you are given two trees, a first tree and a second tree, and what you are asked to compute the minimum diameter after connecting two nodes of these trees. So what can you do here? Okay, so what if you, let's just suppose I connected some node this to this. Okay, now what would my diameter be? Let's try to think. So my diameter would be either the longest path in this tree 1, whatever the longest path we had in tree 1, that is the diameter of tree 1. So either the final diameter would be the diameter of tree 1 only. If even after connecting this tree to this is still the longest path, then it would be d1 only. Okay. Or if this is not the case, maybe the longest path in the second tree, that would be our diameter. So it can be d2. D2 is the diameter of the second tree. D1 is diameter of first tree. So if this is only the longest path, even after connecting, then this D2 would be our final diameter after connecting also. Or maybe we can have a path where this, it can be something like this. Okay. So let me clear this. So if we are connecting this, okay. So what's the longest path? Either the longest path in the first tree itself or the longest path in the second tree, D1, D2. They may be either of these, or we can just try to, if you try to analyze all those paths involving both the trees, so the maximum among all those paths involving both the trees, if we can compute that and say that is D3, then we can just say the max among D1, D2 and D3 is our final answer, our final diameter if we are connecting through this. And then that we can just, now we can just, now D1 and D2 is fixed. If we have two trees, they would have some diameter, they are fixed. Only thing we can minimize is this D3, which is the maximum path when we have connected two nodes, and then a maximum path which is passing through both the trees. That's what D3 is. So we will consider all those paths passing through both the trees. So if we have a path only passing through tree 1, that is already considered while calculating the diameter of T1. If we have a path passing only through tree 2, that's already considered while calculating diameter for D2. So we only need to consider those paths which passes through both the trees, because they are not considered in either D1 or D2. That we have to consider separately, and that only can increase our answer and make it to something greater than both D1 and D2, and that could make our diameter greater. So we need to minimize that thing. Now how can we compute this thing? So let's say I'm connecting this node and this node. So what would my maximum path be between the two trees? So it means I have to, if I have, let's say this one is my root of the first tree. Okay, let's try to understand like this. Let's say I have one tree. Okay, I have one tree. I am showing the tree like this. Okay, I hope you are able to just recognize. So this is a general tree. So these are nodes. Okay, this won't be intersecting. Okay, I'll draw it like this. Okay, so this is some general tree. These are nodes and all. Okay, this is also not intersecting. Now, if you have some general tree and some other general tree, and I am saying that in these two trees, I am connecting these two nodes. Okay, so whatever two nodes I am connecting, I'll just recreate this tree by making that node as the root. So for a undirected tree, you can make any node as the root of the tree. Okay, and then you can just imagine that tree with this as the root. Okay, so just imagine the first tree with this as the root and second tree with this as the root. So what would your maximum path including both trees be? So for that you would come somewhere from the depth of this tree, then goes to here, and then goes to somewhere to the depth of this tree. That would only be your path. So the only way to connect between these two trees is this edge. So for any path passing through both the trees, you would definitely have this edge. So you would definitely pass through this path. And if you are passing through this path, now you have to maximize this length of the path. So you'd go to the maximum depth of here and maximum depth here. So basically, if you are connecting this node with this node, if you can compute the maximum depth you can go after taking this road as the root, and the maximum depth you can go in this tree after taking this node as the root, then the sum of those two depths, I'm telling the maximum depth with this as the uh, root of your first tree is depth 1, and maximum depth with this as the root of your second tree is depth 2. Then your D3, which is the longest path passing through both the trees, the longest path passing through both the trees, that would be depth 1 plus depth 2. And like if you sum up both these depths, then you will also add this thing, this one edge also, so plus 1 to that, plus 1. So your D3 is depth 1 plus depth 2 plus 1. Now how can you compute these two depths? That's your, that's what you need to find, because what you need to minimize this D3. To minimize the your final diameter is going to be D1, D2, D3, the maximum among these three. Now you cannot change this D1 and D2 because you have a first tree and a second tree, their diameters would be fixed. The only thing you can change, that you can decide two such nodes so that when you connect them, you can reduce this D3. So you need to basically minimize this D3. And this D3 is the combination of depth 1 plus depth 2. So you need to minimize depth 1 and depth 2. So basically you have to find for the first tree, the you have to find such a node so that it has minimum. You need to minimize. What do you minimize? Minimum depth, minimum max depth, you can say, because this is not just depth 1, this is the maximum depth 1. Okay, so for the diameter you will consider the maximum depth always. So you need to minimize the maximum depth from that node, taking that node as the root. That's the thing. So if you are calculating like through a tree, so it will, if you're fixing a root, and then let's say you want to connect this node, so you can only calculate for this subtree. You would have to make this node as your root and calculate that. If this is the root, then what's the maximum depth? That would be your, through that you can get your answer. That's the first thing. So if you have evaluated till here, so then the approach that comes to the mind is, you can start for the first tree, you can start for the root, you can calculate the depth using dp. Okay, as I explained, this was the way to calculate depth, but this would give you the depth for each subtree, not when this is taken as a root. Then there is a concept called rerouting of trees. You can do the rerouting of this. So first compute the depth for each subtree. So every like dpx represents the depth for this subtree. Then you can reroute this to make this as the root. Just do the twisting so that you can just watch how you can do it. But we would not require this for this problem actually. Like, one method to solve this is just reroute this and find your answer if this was the root. So if you can find that, then among all the nodes you would take the minimum. Among all the nodes you would take the minimum. Then the sum of those minimums plus 1 would be your D3. Then the max of these three would be your final answer. You can, one approach is solved like this. I had done this in the contest. I had done this BFS rerouting thing, which is a little complicated, but like I had not realized thing. If you like try to analyze it a little more, you would realize that you actually don't need to do that DFS rerouting. You can very easily compute this depth 1 and depth 2 through a formula if you try to analyze a little bit. So let's see what you can do now. Okay. So if you analyze what I did till here, then this DFS rerouting technique is the way to move forward, but it is a little complicated. So if you evaluate it a little more, so what I am telling you is what you can say is what you need to compute. You need to compute that for this first tree that we had, okay, we had one tree, it had some nodes. Okay, so for this first tree, what so for each tree you need to compute, you need to choose such a node so that when that node is the root, it gives you a depth, a max depth, which is minimum among all nodes. Okay, so how can you compute that? So first for root, you can just, what is depth? What is depth when this is taken as a root? Its depth is actually, you go to all its childs, okay, and then just see, check the depths of all its child, get the maximum depth among all its child and do a plus one. That's the depth of this. So the depth of this is the max among all the depths of its child. Okay. So now let's suppose you have found the diameter of this tree. Now, let's suppose you have found the diameter of this tree. First, you have found the diameter. So, let's suppose this is the diameter of the tree, and then I'm redrawing this tree like this so that I have all the other nodes in the center. So, let's suppose this is some tree, and what I am saying is, I am saying that the diameter of this tree is this. Okay. So if this is the diameter of this tree, it means, okay. So let's say there are some more roots here. Okay. So if this is the diameter of this tree, it means for any node in this path, in this diameter, if we are at any node in this path, so if we just analyze any such node, one such node is this. So while calculating the diameter, you know for sure for this node among all its childs, this and this have the maximum depth. One of it is the first maximum, second maximum, because we know diameter is the sum of the top two depths plus something. Okay, so if I'm saying this is the diameter of this tree, then for this node among all its childs, this and this have the maximum depth. Okay, so it means that for this node, which one would have the maximum depth? It would be either this or this. Okay, so one thing I'm telling that the diameter of this tree is d. Let's suppose the diameter of this tree is d. So if we are at some node such that this distance is, let's say, x, then this depth would be d minus x. Okay, if this is x, then it would be d minus x. This is for sure. So what would the maximum depth be? It so if this is x and this is d minus x, so maximum depth is max among x or d minus x, because these are the top two, so the top among them is your maximum depth. So maximum depth is either x or d minus x. So when can you minimize this maximum? So if you are considering all the nodes in this path, it can be minimized when x is exactly, if x is exactly d by 2, then you can minimize. If it is less than d by 2, then one of them would go more than d by 2. With just d by 2, you would take max of d by 2, and d minus x would also be d by 2. So your maximum depth would also be d by 2. So if you are at the middle of your diameter, then your maximum depth would be d by 2. Okay, so for this particular, for the middle of your diameter, you can have a d by 2 max depth. Now let's, so among all these, that's your best case. Now let's also see all the other nodes. maybe you are on some other node which has a max depth which is less than d by 2, then that would be your minimum max depth. Okay, you need to find the minimum max depth. You need to minimize the max depth. So if you are at this at some any other node, what would the maximum depth of this be if this is the root? If this is the root, then all its children would be there, and then one of its children would be this path or this path also. Okay, these would also be its children. So for any other node, it would definitely have this as one of its children. So it would definitely have at least a d by 2 path in it and plus something. So if you take any other node which is not on the diameter, the maximum depth of that is always going to be greater than d by 2. You can conclude that. If you are at any other node, it would definitely have this, the max among these or this. So that can be d by 2. At minimum, that would surely be d by 2, at least d by 2. If it's d by 2 plus something, then for any other node, the max depth is going to be greater than d by 2. And if the max depth is greater than d by 2, then what is the minimum among all nodes? Minimum max depth. It's d by 2 when you take the middle of your diameter. And if d is odd, it's going to be the steal of d by 2, you can say. So if d is, let's say, odd, so let's draw a tree on it with an example. 1, 2, 3, 4, 5. Okay, so it has a diameter of 5, and then 1, 2, 1. Okay, let's say this is your tree. So if you are drawing it like this, it has a diameter of 1, 2, 3, 4, 5. You can take any path. This path would also give you 5, but any other path would give you less. So this is the diameter of the tree, either this or this. Okay. Now let's take the middle of the diameter. So 5 by 2 would give you 2 if you do floor and 3 if you do C. So we would do the, so you can divide this 5 into 2 plus 3. That's the best case if you divide it into 2 plus 3. So let's take 2 and this is 3. So you can take this node as your root. So for this, the max depth is going to be 1 plus 2 plus 2, 3. 3. 3 would be your max depth. And if you take this as the root, then from here you would get 3. So you are going to get a steal of d by 2 as your max depth. So we can conclude that actually this depth 1 is steal of d1 by 2 and depth 2 is steal of d2 by 2. So it just means your final answer is going to be max among d1, d2 and d3, which is d1 by 2 steal plus d2 by 2 steal, okay, plus 1. So the maximum among these three values is going to be your final answer simply. So you just need to compute d1 and d2, the diameter of the first tree and the diameter of the second tree. If you can compute both these diameters, you can get your final answer. Okay, so you simply had to compute both this diameter and find this formula. That was the question. Okay, so now let's look at the code. So what we have here, so we are given the two edges of the first tree, edges of the second tree. So I initialized an adjacency matrix to store that tree. So I have initialized this globally so that I can use in my DFS function. So I'm just making it adjacency.assign. So I'm computing the size of the first tree is number of edges in the first tree plus 1 is going to be the number of nodes in first tree, and number of edges in second plus 1 is number of nodes in second tree. So for the first tree, I'm computing my diameter. It would be adjacency. So I'm assigning it a size of n and just I'm creating my adjacency matrix. Okay, so for every edge, I'm pushing bidirectional edge into my adjacency matrix. So I've created my adjacency matrix. Then I've taken this depth vector which I'm assigning to -1 initially, and I'm taking this diameter as 0, so I would just maximize my sum of the top two depths to get my diameter. Okay, so we'll see how we are doing in the DFS. So 1 point, just we can assume any root. So I'm assuming 0 as my root and starting my DFS from there. So with that as the root, I'll initialize my depth of that node to 0. And what's my transition for depth? Depth of a node is actually depth of that node or depth of child plus 1. So maximum among all its child. So initialize with 0. So among all its child, the maximum depth of child plus 1. We have just initially maximized it with depth of child plus 1. That's what my depth of a node is. It's depth of child plus 1. So I've calculated the depth of my node by by doing the DFS traversal to every child, and then I have to calculate the top two depths. MX1 is the maximum depth, MX2 is the second maximum depth. So in val, I'm showing the depth of child plus 1. As I told, I'm doing the plus 1 in MX1 and MX2 only. Okay. So I'm actually showing the depth of child plus 1. So if depth of, so I'm, this is the way to compute the top two. So if val is greater than MX1, we'll change MX, the second maximum will make it as the first maximum, and first maximum would be val because this is greater than the maximum one. And if this is greater than just the second maximum, this is second. So in this way, we are computing the top two values of val, which is depth of child plus 1, and then my diameter would be just max of diameter comma mx1 plus mx2. Okay, this way we are computing the diameter as I explained. So diameter is just mx1 plus mx2. So mx1 and mx2 are the top two values of depth of child plus 1. Okay, and my depth of child transition is this max amount depth of child plus 1. This is the depth of a node. So this way we are calculating the diameter. So I've initialized this global variable diameter. So in this way I'm calculating the diameter for the first tree. So I've called DFS for first tree, and D1 gives me the, so in dia I have got the diameter first tree, I stored it in D. Now I'll use the same functions to calculate diameter for second tree also. I've just cleared this adjacency matrix. Now I'm creating the adjacency matrix for the second tree. So I have just used that variable, that adjacency matrix only to recreate the second tree. I've cleared the first tree and inputted the second tree, and then I've cleared that depth matrix, depth vector also. And again, I've called DFS, initialize diameter to 0. Now, after DFS, my diameter would be calculated. That would be my D2 diameter of second. So, like this way, I've just used the same DFS function to calculate diameter of both of them. You can do different DFS functions so that you can have different variables if you wish. Okay, so this way I'm just computing the diameter of first tree, diameter of second tree. My final answer is max among either D1, D2, or the seal of D1 by 2. You can write is D1 plus 1 by 2. This would give you the seal, because if you have an even case, let's say 4. So 4 plus 1 by 2 would also give you 2, and 4 by 2 would also give you 2. So for 4 even case, it's okay. But for odd case, if you do 5 by 2, the floor division it give you 2. But if you do 5 plus 1 by 2, it would give you 3. It would give you the seal. So for doing the seal by 2, you just do just d1 plus 1 by 2. You will get the seal of d1 by 2. If you had to do the floor, you would just do d1 by 2, because d1 by 2 would just give you the floor integer of that. Okay, so seal of d1 by 2, seal of d2 by 2 plus 1. This is my d3. So I've maximized d1, d2, d3. This is my final answer. So this was the explanation for the third problem. And as I told, like if you didn't, if you were like during the contest, I was not able to get this formula. I had just the initial intuition that I explained, the maximum depths and all. Then I just did the DFS rerouting thing and calculated this. Just after the contest, I realized that we can do like this also. So I explained the simpler version. But if you want to like read about the DFS rerouting code, I'll attach that in the description, the rerouting code also. You can refer that. But this is a more simpler way to solve this problem. If you wish to just take a look at the a little complex way of rerouting technique, you can take a look through. I'll attach that in the description, the second code. Okay. So this was it for the code problem, and this was our discussion for the Leetcode Weekly 404. Hope you liked it. Thank you very much.